It's time. Okay, so please take a look at that stuff I just had typed into you guys about homework due Friday, and then homework and a take-home test due on take-home quiz due on Wednesday. The test is on Wednesday on 11.1 through 11.10. I've got a practice set that's posted on Blackboard if you don't have a hard copy of it, and the solutions to that. I'm not collecting that. The solutions to that will be posted on Blackboard sometime Sunday afternoon. Also, you should, if not today, very, very soon, have available the facts and formulas that you need to know for this test, and also a handout called Important Series. So this is the facts and formula handout right here, and then Important Series handout right here. The good news on this, I want to try to give some good news here, is that the Important Series handout, this one here, this will be attached to the back of your test so that you don't have to memorize the formulas for those series that are given there, all right? Again, unless you demand that I not do that. Okay, so we're on section 11.9. Does anybody have any questions on homework? Maybe I should open that door a little bit. Okay, why don't you give me what the problem is, or just come up and show it to me so I can copy it down.
Well, the infinite sum of n to the n power times x to the n power.
What is it? N to the n power
Times x to the n power.
Oh, it's times x to the n power. Okay, and then what's it over?
That's it.
Oh, that's it.
Yeah, give us the hint to use the root test.
Yeah.
So then it comes out the absolute value of n times x.
Okay, oh sure. Okay, so this, we want to find out, does this thing diverge or converge? I assume n is going from 0 to infinity, and then we have both, this is just represented as a power of n, so I'm hoping that you would see, and that's in my strategy handout, to look at the root test as your first choice here. So we look at the nth root of n to x to the n times n to the n, and we take the limit then as n goes to infinity. Well, the nth root of that is just going to, and this is the absolute value, by the way. So the nth root of that is going to be the absolute value of x to the first times n, and we look at that limit as n goes to infinity. All right. Okay. Now, what happens if x is some non-zero number as we take this limit as n goes to infinity?
Which is going to infinity.
Yeah, sure. If x is 1/2, it's going to go to infinity. But what happens if we have the one case where x is equal to 0? What's the limit going to be?
Well, it does start at n. N starts at 1, not 0.
Okay, it doesn't matter. What if x is equal to 0 then for this limit? So I'm looking at this. If you plug in a 0 for that x, what am I going to get for my limit? Now wait a minute here. Let's look at this. If we're looking at the case where x is equal to 0, we're looking then at the limit as n goes to infinity of 0 times n, which is just 0. Don't make it any harder, all right? So this is the limit of just plain old 0, and now we don't even have an n. The only thing that limit can be is 0, right? Do we see that? Don't make it too hard. So therefore, the key here is only when x is equal to 0 do we have a limit that's less than 1. So what's the only value that we have in the, shall we say, the domain or interval of convergence for this function?
0.
Just 0. Plain old one number 0. And that's it. Okay. Anything else? You guys out there, you've all finished the homework? No problem? I hear from one of them after every class. He gives me his critique of the class. But normally, it's been a while, actually. But I know they're out there. Okay, well, I guess we're good to go then, so far on the homework then. All right, let's go back then to this section 11.9. All right, so the key concept here is we're trying to get power series representation of some kinds of functions. And the key concept here is this one that I've rewritten up here at the top here, that 1 over 1 minus u is equal to the summation of u to the n power as long as the absolute value of u is strictly less than 1. And of course, this is a geometric series. All right. And we're using the central fact to obtain other power series representations. So here's a problem where we are asked to express 1 over 1 plus 2x squared in the denominator as a power series. Find its interval of convergence. Now you look at this thing, and you see that we have a square down here in the denominator. Oh, I think some of you guys have your mics still turned on because I'm hearing something. I'm hearing voices again. Yeah, okay, thanks, Jennifer, for validating that I'm not becoming schizophrenic today. So turn off your mic. Don't ask me how you turn it off. I'm way over 30. Okay. So we've got a square in the denominator. Our aim is to get something that looks like this, all right? So we know when we take an integral of something, we increase the power by 1. So let's look at this. The integral of 1 over 1 plus 2x in parentheses squared dx. And let's see what we get here and what it can get us. Okay, I'm not going to use the letter u because I don't want to, because we have a letter u up there already. Let me use the letter v. And so we're going to do a substitution. Let v equals 1 plus 2x. And therefore, dv is equal to 2 times dx. And dividing by 2, dx is equal to 1/2 dv. So I can convert this with substitution into 1/2 times 1 over v squared dv. All right. Okay, and we can get this antiderivative. This is really 1/2 times v to the negative 2 dv. And we're going to add 1 to the exponent, divide by the same. So this is going to give us 1/2 times v to the negative 1 power over negative 1 plus some capital C. And in fact, actually, for right now, I'm not even going to worry about the capital C. And then let's see what this gets us. Let's bring the -1 out front. So we have -1/2 times v to the -1, which is going to be -1/2 times 1 over, now v is equal to 1 plus 2x. Okay. So this is what we obtained then as our antiderivative, -1/2 times 1 over 1 plus 2x. Now this is something that I can work with to get it in the format 1 over 1 minus u. All right? And the way to do that is that little trick with double negatives. Right. Okay. Double negative, so I can rewrite this as -1/2 times 1 over 1 minus the -2x. All right? Just that little trick making a double negative. So therefore, this minus 2x is going to be my u. So therefore, this then I can rewrite using my formula as -1/2 times the summation n equals 0 to infinity of, it's u to the n, so it's going to be minus 2x in parentheses raised to the n power. And this is going to be okay if that absolute value of -2x, my u, is less than 1. All right? Now, what this is going to tell us is that the absolute value of 2x has to be less than 1. And so if I divide both sides by 2, this means that the absolute value of x has to be less than 1/2. So therefore, my x's are squeezed between positive 1/2 and negative 1/2. Like this. And that would be my interval of convergence. Interval of convergence. Okay, but we're not quite finished with this problem yet. Let's get another piece of paper here. So what we have found out is this, that the integral of 1 over 1 plus 2x in parentheses squared dx, we found that it equals this power series, -1/2 times the summation n equals 0 to infinity of -2x raised to the n power, as long as the absolute value of x is less than 1/2. All right. But this isn't what, yes, Jenna? We don't need to test the points here, because for geometric series, it only converges inside the interval. So there's no need to test the points. But let me go way back here, up here to where we started. This diverges if the absolute value of u is bigger than or equal to 1. Geometric series. So we only have to go, we don't have to test the endpoints. All right, let's go back to this. So we're asked for the representation of 1 over 1 plus 2x squared. We found now what the antiderivative is, or what the integral of it is. So therefore, 1 over 1 plus 2x in parentheses squared is going to equal what of the other side? The derivative, right. This is the antiderivative. The antiderivative of 1 over 1 plus 2x squared. So to get to 1 over 1 plus 2x squared, we have to take the derivative of this. Everybody okay with that? So this is going to be -1/2. Now I tell you what, Okay, we'll do it this way. Now remember, we can take the derivative term by term, right? So let's do the summation, and we're going to find the derivative of minus 2x to the n power dx. We can do it term by term. All right, now the easy way to do this inside is this. Separate out the minus 2 from the x. So this is going to be the derivative of minus 2 to the n power times x to the n power dx. And then we just use our basic power rule for derivatives, bring down the exponent, and subtract 1 from it. So it's going to be minus 1/2 summation from 0 to infinity. Okay, the minus 2 to the n is not going to change. That is a constant. We're not going to be reducing its exponent by 1. All right, that's a constant. But the x here, I'm going to bring down the n and then lower it to x to the n minus 1 power. All right. And then this here is a good enough answer. All right. That is my power series representation. So this is we had an example like this at the end of class last time, where again we had to do an integral first to get it in that, so that we can make it as 1 over 1 minus u, and then we had to find the derivative to get back to the original function. Okay. Question on that example, that process. Okay, let's look at something else then, where we have to go the other direction. So this one is find a power, I'll just PS, power series representation of the natural log of 1 plus x and get its interval of convergence. And get its interval of convergence. All right. Okay. Now, remember what we want to try to get. We want to try to get something that looks like 1 over 1 minus u. And we're working with the natural log. What happens when we take the derivative? What's the derivative of this natural log? It's equal to 1 over 1 plus x. Aha! I can get that as 1 over 1 minus u. Let's just rewrite it as 1 minus a negative x. And this then is my u. So we can write that as a power series. So this can equal then the summation n equals 0 to infinity. Now this time it's going to be in parentheses negative x raised to the nth power. And this is if that absolute value of negative x, my u, is less than 1. So that, of course, means that the absolute value of x has to be less than 1, which means that x has to be squeezed between negative 1 and positive 1. And we do not have to check the endpoints for this geometric series. All right. Now, so we have this. So this is the derivative of the natural log of 1 plus x. But we're, yes?
But if you did do greater than or equal to 1.
It diverges if that absolute value is bigger than or equal to 1. Okay, wait a minute now. Hold. Where you say there's a 1, Kyle? Where are you talking about? Here? Yeah. Okay. But those are parentheses. This is interval notation. All right? This is not this is not the set of two numbers, minus 1 and 1, all right? Interval notation. So this is everything between the two numbers, okay? All right. Okay, Jenna?
Right, it's probably a really stupid question, but how do we know that the element of some type is geometric?
How do we know that it is? How do we know that it is? Well, we don't. We're going to find out that it is. Okay, I'm a little confused about.
You said it's, you don't have to test the point that it's geometric series. So how do we know that?
Oh, how do we know something is a geometric series? Okay, that's your question. A geometric series is something where every subsequent term is multiplied by a common ratio. So this thing right here, this summation, when n is equal to 0, anything to the 0 power is 1, right? When n is equal to 1, then it's negative x. And then when n is equal to 2, it's minus x in parentheses squared, so it's plus x squared. And I'll just do one more. When n is equal to 3, we have an odd power, so it becomes minus x to the third power. If you look at this, you can see that every term is, we multiply by negative x to get the next term. That's a geometric series.
So the only way to know that is to write out two terms.
Well, that's one way, unless you can just see that, well, okay, if you have to do that, then do that. All right, that's all I can say. All right, let's get back here then to this. We've got that the derivative of this natural log expression is equal to that power series. So how am I going to find the representation of just the ln? Take the antiderivative. This is the other case. So so therefore the ln of x plus 1 is equal to the antiderivative. So I'm going to do the integral of this summation minus x to the n power dx. N goes from 0 to infinity. All right. Now the thing is, we can do this antiderivative term by term. So we can write this out then as the ln of x plus 1 is equal to the summation. We can put our summation next and then do the antiderivative of each of the terms, which is minus x to the n power. Bring it inside, do the antiderivative term by term. Now for this one here, there's an easy way and a harder way to do this. What's one way you can approach this that doesn't involve trying to do a U substitution? Exactly. Cassandra says just split it up, and that'll work very nicely here. So let's rewrite this as a summation n equals 0 to infinity, antiderivative. Now we're just going to write this as minus 1 raised to the n power, and then plain old x raised to the n power. And that makes it easy then. All right. So let's continue with this. We have summation n equals 0 to infinity. Now again, the minus 1 to the n, I'm just going to keep as it is. It's a constant. So minus 1 to the n. Don't be fiddling around with that. But the x, we know we raised the exponent by 1, and then I put it over the elevated exponent of n plus 1. All right. So this then, and now this time around, though, I do have to add on a plus c. So this is plus c, because we're trying to find an antiderivative. Okay. So we've got a power series right here. I want to try to figure out what this c is. The easiest way to do it is to just plug in 0 for x, and you'll get a value for c. plug in 0 for x, and solve for c. So when I plug in 0 for x on the left side, I just get the ln of 1. And what does the ln of 1 equal to?
0.
0. And then I go to the right side and I have this summation. Now, my first power of x is 1, because it's x to the n plus 1. So this is all going to be 0 to the n plus 1 over n plus 1. Well, that whole summation is just going to equal 0. And then I have a plus c. So therefore I have 0 has to equal c, and that's what my value is then. The c is equal to 0. So I guess I can say my final answer then as far as the power series is the natural log of 1 plus x is the summation as n equals 0 to infinity minus 1 to the n times x to the n plus 1 all over n plus 1, as long as if the absolute value of x is less than 1. Okay, we're going to do another one which is similar to this one, but it involves us having to do a little bit more manipulation to get the 1 over 1 minus u. Any question on this last one here? So you have to recognize though that when you do the derivative of a natural log, you get something over something, and that's what's going to help you out here. All right. Let's look at this one here, where, again, we're trying to find a power series representation. Again, it's of an ln. It's of the ln of, in parentheses, 7 minus x, and get its interval of convergence. And get its interval of convergence. Okay. So again, we're going to take the derivative of this and work with the derivative. The derivative of the ln of 7 minus x, okay, the denominator is going to be 7 minus x. What am I going to have in the numerator? Minus 1. The derivative of the denominator. So I have minus 1. All right. Now, this is what I want to get in my general format of 1 over 1 minus u. Yes?
How do you do for n negative 1?
Okay. We're using the chain rule here, all right? Derivative of the natural log. If, say, we have the natural log of just some expression v, and we want to get its derivative with respect to x, it's equal to the derivative of the v over the v itself. This is using the chain rule, right? So that's what we've got here. This is our v here. We just put the 7 minus x in the denominator, but then we have to find in the numerator, we're going to be putting the derivative of 7 minus x from the chain rule. Okay. So anyway, now Will had an interesting way of doing this. The last time, I'm going to want to go with the way that I do it, the way the book does it, all right? So what I can do here with this thing, I've got that minus 1 on top, is in the denominator, I can draw out a 7, all right? And so the first 7 there in the denominator then becomes a 1. And then with my second term, what do I have to write as my second term then? X over 7. All right. So I can rewrite then minus 1 over 7 minus x as minus 1 over 7 times 1 over 1 minus x over 7, like that. Kind of separate it apart a little bit. And then this gives me my 1 over 1 minus u format. Okay? So I can write this as a power series minus 1 over 7 times the summation n equals 0 to infinity of x to the 7th power in parentheses, x over 7 in parentheses raised to the n power. And that's if the absolute value of x over 7 is less than 1, right? It's less than 1, which means when I multiply both sides by 7, the absolute value of x has to be less than 7. So therefore, x is squeezed between negative 7 and positive 7, like this, interval notation, and I don't have to check any endpoints. All right. So we found here then that the derivative of the natural log of 7 minus x is equal to this power series here. So again, I then take the antiderivative of the right-hand side. So therefore, ln of 7 minus x is going to equal minus 1 over 7 times the antiderivative of this summation of x over 7 to the n power. And again, we can do this term by term, so I can put that interval sign on the other side of the summation of this integral, and I want to rewrite the integral also to make life a little bit easier for myself. So how can I rewrite x over 7 raised to the n power as x to the n power over 7 to the n power, right? Just break it apart. And that's dx, right? And let's go on, and we're going to need to tack on a plus c on this. So let's go on and tack that on. All right, so this is then an easy antiderivative to get after we broke it apart. So I have minus 1 over 7, n equals 0 to infinity. Okay, the 1 over 7 to the n is a constant. We don't mess with it, so I just rewrite it, 1 over 7 to the n. And then I do my antiderivative of x to the n, which is x to the n plus 1 over n plus 1, plus the c. So here we have it then, and this, of course, is if the absolute value of x is less than 7. All right, so this is our power series. The only other thing we want to look at here is what is my value of c. So let's plug in 0 for x. So we get ln of 7 minus 0, or the ln of 7, is equal to, now this whole thing, when I plug in 0, it's just going to be one big 0, and then I have my plus c. So my c is equal to the ln of 7. All right. So my answer is the whole power series plus the natural log of 7, and that's my answer then. Okay. Okay, we've got two more things here for this section that I want to go over. This next one is just using a different kind of function, but we're going to do the same kind of thing we just did. We're going to take a derivative of it. And the function that we're going to look at here to express as a power series is the arctan function, tan inverse of 1. So the question here is to express tan inverse of x as a power series and get its interval of convergence. Okay, so what do we know about the derivative of the tan inverse of x? One over 1 plus x squared, right. So we know this, derivative of the tan inverse of x is equal to 1 over 1 plus x squared. Aha! I can fiddle with that and get that into the 1 over 1 minus u format. And I do that little trick of doing the double negative. So I can rewrite this as 1 over 1 minus a negative x squared. And so therefore minus x squared is my u. So this then can be my power series, n equals 0 to infinity, in parentheses, the minus x squared raised to the nth power. And this is going to be good if that absolute value of minus x squared is strictly less than 1, and that's going to hold if the absolute value of x itself is less than 1, or in other words, x is squeezed between minus 1 and 1. Okay? All right. So we've got this fact here. The derivative of the tan inverse of x is this power series. And I think right now I'm going to do a little fiddling with this thing just to make my getting my derivative a little bit easier. So let's think of another way that we can write minus x squared in parentheses raised to the n power. Minus 1 to what power? And minus 1 to the n power, right? Yeah. Minus 1 to the n power, and x 2 times n. When we take a power to a power, we multiply the exponent, so it's x to the 2n power. And that'll make it easier when we get the derivative then. All right. So therefore, I'm sorry, we're going to get the antiderivative. Excuse me. So therefore, if the derivative equals that, then the function itself is going to equal the antiderivative of this, of minus 1 to the n, x to the 2n dx, as n goes from 0 to infinity, plus some general constant c. Right? Okay. So this hopefully should not be a difficult antiderivative. So actually I can put the antiderivative or integral inside. So I have the summation from 0 to infinity of the integral of minus 1 to the n, x to the 2n dx, plus our c. Okay. Right? And then do the antiderivative. So this is the summation. Okay, again, I'm not going to be fiddling with the minus 1. That's going to stay minus 1 to the n power. But then I raise my exponent by 1 and divide by the same. So this is x to the 2n plus 1 divided by 2n plus 1. Okay, plus our c. Okay. And what do we think the c is going to equal to here? If I plug in 0. It's going to equal 0. Tan inverse of plug in 0 for x. I'm sorry, plug in 0 for x. Tan inverse of 0 is 0. This is 1 big 0 plus c. So c has to equal 1, 0. All right. Okay. All right. So sometimes you have to do these little tricks. You either have to remember the whole focus is to get that format, 1 over 1 minus u. Sometimes you have to do a derivative to get it. And in the first couple of examples that yesterday and today, we had to get an integral to get it. And then we go from there. The last thing I want to do is actually shows one kind of interesting thing here as far as finding antiderivatives. So this is the problem. Evaluate this antiderivative, the integral of 1 over 1 plus x to the 7th dx, as a power series. Now for starters, say you didn't know anything about power series at all, and you had, on a homework or a test, figure out the antiderivative of 1 over 1 plus x to the 7th power. Any ideas on what we would even try to do if we... Some kind of substitution, maybe even a trig substitution. Tell you what, I don't know. So I don't know what that antiderivative is through the substitution ways that we've had, all right? But if I can represent this right here as a power series, I'll be able to get the antiderivative, all right? So let's just first of all look at 1 over 1 plus x to the 7th. And remember our guiding formula, 1 over 1 minus u. So what's going to be how am I going to rewrite this? Double negative, right. 1 minus negative x to the 7th power, double negative. This then is the u. So I can say that 1 over 1 plus x to the 7th is equal to the summation from 0 to infinity. In my parentheses, I'll put a minus x raised to the 7th power to the n power. And this is as long as this is valid if that absolute value of x to the 7th power is less than 1. And the only way that's going to work is if x itself is between minus 1 and plus 1. Or minus 1 in parentheses plus 1. Okay. All right. So let's then, so therefore what we need to do then, this antiderivative then is going to be the antiderivative of this power series, n equals 0 to infinity of minus x to the 7th power raised to the n, dx, all right, plus a c. And so, let's bring the integral inside. We can do it term by term, so it's n equals 0 to infinity of the integral of, let's rewrite this. I want to make life easy. How can I rewrite this to make my antiderivative be much easier? Minus 1 to the n times x to the 7n, right? Be a nice, easy antiderivative to get down. Okay, everybody see that? Just doing that little fiddling with exponents. All right, so now this is going to be my summation. And now I get my antiderivative, the minus 1 to the n. Again, I can't emphasize that enough. That's going to stay as it is. And now I raise the exponent by 1, so it's going to be 7x to the 7n plus 1 over the same thing, 7n plus 1. And then that'll be plus my capital C. And this is my answer then. My answer for this is a power series as long as the absolute value of x is less than 1. No, because on this case, we're just finding an antiderivative, so we just keep the general plus c. All right, we're not solving for it. Okay. All right. Why don't we take a 5-minute break then, and we'll get started on the last section. The last section, not the last section of the semester. Kyle. We were going to end like, this is it. We're going to just play games for the rest of it. That would be great. Not really. You can enroll in the curriculum. done all the important stuff. I think we've done the hardest stuff.
No.
Mm-hmm.
Why did we skip to the end?
You know what? I teach this Introduction to Differential Equations at Uncle, and they've all had 3 semesters of calculus as a requirement to take the class. They're mainly engineering students. And so I asked them, of the 3 semesters of calculus, which one is the worst?
Semester 2. Yeah, that's the.
Why did everyone say that?
Huh?
What about these formulas we always have to know?
Without a doubt, F201. She had abandoned me this semester because she found sabbatical. But no hesitation at all.
With the difficulties calculus Texas do have it, apparently Texas freaking easier comparison. By the way, why did we skip from chapter 6 to 11 again?
Because that is how I've seen other teachers whom I respect teach Calc 2, right? And it seems like it's a good idea to get this whole big thing over with, and then we just have a couple of other little chapters to do, rather than putting this off to the bitter end, this serious stuff. So anyway, apparently it's worked, apparently through trial and error, it's obviously worked better for them to do this one now. So I'm not going to reinvent the wheel.
How many chapters?
Well, we go back to chapter, let's see, we did 6 and 7, then we went to 11. So we're going to do some stuff in 8, then there's 9, and then there's 10, but some of those are going to be kind of brief. So there's 8, 9, and 10, I think, left. And it sounds like a lot, but it's not really much because we're not going to fully cover all the stuff in those sections. So. Because we're over half, obviously we're half done, as it is.
And that would be half, only times 3.
So. I don't know if that's any encouragement to you guys that everybody agreed that this was the worst of the 3 semesters.
Are they teaching us next semester? Or is it Calc 3?
Do you teach Calc 3?
As of right now, that's the plan.
I'm sorry, but I'm back there.
Oh, you're going back to Merrimack
I'm
County?
30 minutes and still being late because of traffic.
Okay, all right. Just be that way.
Well, it's like a 5-minute drive.
Oh.
I do like this campus pretty nice, but not, people aren't nearly as friendly.
What's this now?
Merrimack feels more like college. It
Yeah,
feels like high
Merrimack
school.
feels like college.
Yeah.
When I came here, I'm like, one building?
Yeah, I
What?
like
I mean, I think it's small.
It is very small.
It's much more. I like how everything doesn't break down all the time, except for like, computer problems, but that's everywhere.
It doesn't feel like college coming here.
So you're getting back to Merrimack next
I
semester
take
too?
classes at both campuses. Because I live literally halfway between both.
Good.
Yeah, that's fine.
Well, I hope as many of you as possible can join me again next semester, but trying not to take it personally if you don't. But
I would.
I might find out where you live. Okay.
You start teaching at Merrimack.
I'm usually one of these people that once I get someplace and feel comfortable, I can stick around rather than move around. So.
Fair enough.
Yeah. This last section here, we're still going to be talking about power series, and we're going to be talking about representing a function again as a power series, but it's a more general way of doing it than the very particular way that we did in the last section. The last section we had, it all was centered around this 1 over 1 minus u and getting a power series representation that way, all right? So this is going to give us a power series for a more general class of functions. Or general class of functions. Okay. Now, so what I'm going to do here is kind of develop the idea of this thing called a Taylor series. And so we're going to start out by assuming that our function, we're just going to use the generic f of x. We're going to assume that it can be represented as a power series. So assume f of x can be represented as a, and of course, when we say this, we're always talking about a convergent power series, because if it doesn't converge, there's no value. All right. Let's assume it can be represented as a convergent power series about the number a, and we'll have the radius of convergence where for x minus a, the absolute value of x minus a less than some number r, this is our radius of convergence. Okay. So it holds for some values of x around that number a. So this is what it would look like then. So we're assuming it can be done like this. So therefore, f of x, let's just write out a few of the terms here of the power series. We'd have c naught plus c1 times x minus a to the first power plus c2 times x minus a to the second power plus c3 times x minus a to the third power. And I'm going to go out one more, plus c4 times x minus a to the fourth power. And then I'm just going to put a plus, plus, dot, dot, dot. All right? Because it'll go out to infinity. Now, we're going to try to figure out what these coefficients are. What c naught, c1, c2, c3, etc. equal to, what they're equal to. All right. So first of all, I'm going to take this representation right here, and I'm going to plug in a for the variable x. For x. So I get this. Instead of f of x now, I have f evaluated at a equals c naught plus c1 times a minus a plus c2 a minus a squared, etc. Notice that by plugging in a, all the terms after the first one just equals 0. So therefore, f of a, this is 0 and 0 and all out is 0, f of a equals c naught. Now, in math, there's a convention that 0 factorial is equal to the number 1. Okay. By definition, 0 factorial is equal to 1. All right? Because it's nice and convenient, actually, to have it that way. So therefore, this, what we have here is we have c naught then is equal to f of a, and we could say it's divided by 0 factorial. All right. There's a reason I'm doing this when we go to the other ones, okay? All right. Now let's find f prime of x. Let's do the derivative of this power series. So when we do that, the C naught goes to 0 up here, and what I have over here then is a C1, because that exponent goes to 0, and then I have plus 2 times, I bring my exponents down, 2 times C2 times x minus a to the first power, and then I bring down my exponents again, plus 3 times C3 x minus a squared, plus 4 times C4 x minus a to the third power, and I continue out like that. Okay, so that's my derivative, and now let's again plug in a for x. Right. So I get this, f prime at a, well, I have my C1, and then for all the other terms, when I plug in a, I just get a 0. So it's plus 0. Plus 0, plus 0, plus 0, etc. Okay, so I can say, therefore, that C1 is equal to the first derivative of f evaluated at a, and now I'm going to put this down in the bottom. This time, though, I'm going to put 1 factorial. Well, we know 1 factorial is just equal to 1. All right. Now let's do the second derivative. So now let's find f double prime of x. So we just work off of our first derivative to do that. The C1 is going to go to 0. Now this term is going to become 2 times C2. This will be x to the 0 power, so that's a 1. And then plus 2 times 3, 6 times C3 times x minus a, plus 4 times 3, 12 times C4 times x minus a squared, and plus dot, dot, dot. So I'm just doing the derivative term by term. And again, now I'm going to plug in a for the x that I get there. All right. So now I get f double prime evaluated at a. Okay, 2 times C2 is going to be carried down, but my other terms are all going to be 0 because they still have the x minus a in them. So I get this representation then. C2 is equal to f double prime at a over 2, but 2 is the same as 2 factorial. So I'm going to put it that way. It's 2 factorial in the denominator. And I'm going to do this one more time so that we can make sure that we understand that we have a pattern here. So now I'm going to find the third derivative of x. So I'm going to go off of, use my second derivative. My first term, 2 times C2, is going to go to 0. And here I've got 6 times C3, and that's going to be to the 0 power, so it's 1, plus 12 times 2 is 24, C4 times x minus a to the first power, and then it's plus dot, dot, dot. All right. Again, we're going to plug in a for x. And I get the third derivative of f evaluated at a is going to equal 6 times C3, and the rest of them are going to end up being 0. So we can then say that C3 is equal to the third derivative of f evaluated at a. Now we're dividing by 6, but 6 does equal 3 factorial, 3 times 2 times 1. Okay, so this is what we have here. We have C naught is our original function at a divided by 0 factorial. C1 is the first derivative at a divided by 1 factorial. C2 is the second derivative at a divided by 2 factorial. C3 is the third derivative at a divided by 3 factorial. So hopefully we can see a pattern here that the nth coefficient here, Cn, is going to be the nth derivative. So this is the way I would represent it, f with that superscript n in parentheses, the nth derivative evaluated at a divided by n factorial. So I can write, so my function f of x can be written like this. Okay, we said it was a power series, c sub n x minus a to the nth power from 0 to infinity, but we know what those cn's are now. This can be the summation as n equals 0 to infinity. Now for those cn's, I'm going to put the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power. And this is for absolute value of x minus a less than some radius of convergence. If you look on that important series handout there, this is the second from the bottom. This is a Taylor series representation. So this is called a Taylor series of f of x, and then we could say about the number a, or around the number a, or at the number a, or even centered around the number a. Lots of different terms that you can use here, but it's the Taylor series around a. Okay. Now this is assuming that it converges, all right? Now the text talks about a test that you can do to test for convergence. We're not going to get into that, all right? I guess the point, though, that I want to make is we can't, although for our purposes they're going to converge, but we can't necessarily always assume that that's the case in general, okay? But the ones that we're going to look at will converge. Now, we have a special case of this. Instead of having a general number a, if a is equal to 0, we have what is called the Maclaurin series. So if our number a is equal to 0, then we have, okay, we have our f of x is equal to the summation n equals 0 to infinity. Now instead of f, the nth derivative at a, we're going to put the nth derivative at 0 over n factorial. And then instead of x minus a to the nth power, we're just going to have x to the nth power. All right. And this is called the Maclaurin series. So if you're asked on homework or a test to do some kind of Maclaurin series, that means you're using 0 instead of the general number a, right? We can basically say that a Maclaurin series is a Taylor series centered at 0. Is a Taylor series centered at 0. All right. Okay. So what you see here, instead of worrying about getting in that 1 over 1 minus u format, if we've got functions that we can get the derivatives of, and as long as it converges, we can get this kind of power series representation just by filling in the dots here, okay? So let's look at some examples of this type of thing. Yes?
I just have a question. I mentioned that we are normal, right? But why isn't it just equal to 0?
What's that? Oh, it's centered at 0. Okay. Yes, you're right. When x is equal to 0. Okay, let's look at what this is. Let's write this out a little bit. This is f of x equal, okay, when n is equal to 0, so we do a summation. First one is n is equal to 0. So the first one is this. We're going to call f0 is the same as just our function. All right? That's just a convention we're going to use. Because for 0, we're not taking a derivative. It's just the original function. So our first term is f of 0 divided by 0 factorial times x to the 0 power, which is just 1. And 0 factorial is the same as 1. And then we have, let's just look at another term, then we have n equals 1. This is the first derivative evaluated at 0 over 1 factorial times x to the first power, plus then the next term, f double prime is 0 over 2 factorial times x squared, etc. All right? So what is the value of this if I plug in 0 for x, Jenna, what am I going to get for my value of f of x? Not be guessing around. All right? If I plug in 0 for x, so I have f of 0 equals f of 0 plus what? 0 plus 0 plus 0, etc. All I get is this identity, that whatever f of 0 is, that's what f of 0 is. It doesn't have to be 0 or 1, okay? But it's not exactly 0. It's whatever f of 0 is. Do you know the difference? If f of x is equal to 1 plus x, what's the value of f of 0? Okay, right. So you know how to get f of 0, and it's not necessarily going to be 0 or 1, all right? Okay, so let's look at some concrete examples rather than just theory here. So here's the first one. Find a Maclaurin, so here we're talking about those zeros, series for f of x equal e to the x, and let's also find its radius of convergence. Okay, so we picked a nice function, e to the x. Why is e to the x so nice? Right, its first derivative is e to the x, its second derivative is e to the x, etc. So that's a nice thing about e to the x. So, therefore, the nth derivative of e to the x is just equal to, well, that's a quick, wait a minute. The nth derivative of x, then, is always going to be e to the x. All right, it just repeats itself. Now, this is a Maclaurin series, so we're going to be looking at f, the nth derivative evaluated at 0. So that's going to be e to the 0 power, which is equal to 1. So all of those nth derivatives in our Maclaurin series are all evaluated at 0, are all just going to equal 1. Okay? So let's write, so e to the x is equal to this summation. Let's first of all just write it out more formally. From 0 to infinity of the nth derivative of 0, because we're doing a Maclaurin series, divided by n factorial times x to the n. Now, all of those derivatives are equal to 1, so, and including the original function when we plug in 0. So this is the summation n equals 0 to infinity of 1 over n factorial times x to the n. Okay? So this would be something like, when n is equal to 0, this will be 1 over 0 factorial, and then plus, when n is equal to 1, it'll be 1 over 1, so it'll again be 1 times x to the first power, and then it'll be, when n is equal to 2, it'll be 1 over 2 factorial, which is just 2 times x squared, and let's do one more. When n is equal to 3, it's 1 over 3 factorial, which is 6 times x to the third, etc., like that. Okay. So this right here is the answer to the first part about finding a Maclaurin series representation. If any of you have looked yet at the, did I put it away? Yeah. Here, let me make sure. Let me dig out something here. Oh, yeah. If you've looked at all at the take-home quiz, you'll see that on a couple of these, I provided you with a little table to kind of help you. All right? So therefore, I've got, here I'm asking for the first 4 terms of a Taylor series. So I've got a table where n is going from 0, 1, 2, and 3. That'll give us 4 terms. You write in what the representation is of the derivative. And again, I want to remind you guys that what our notation is going to mean that f, the 0 derivative of f, if we want to call it like that, is just equal to the function itself, all right? That just helps with the notation. So you just write in your derivatives here, and then you plug in the value that I want you to use for a. So you evaluate, in this case, you get your derivatives, you then plug in pi over 4, you get your value. So that gives you the value of the nth derivative at a. And then you continue to, then you use the rest of your Taylor series formula to give the first 4 terms, all right? So, and I've got that on a couple other ones, at least, well, one other one here on the practice quiz, all right? I'm at the practice quiz. How about the take-home quiz, okay? Well, it is kind of a practice quiz also. All right, so we found, so any question about, first of all, about how we found the Maclaurin series representation of this? Now, the second question is find its radius of convergence. So we've got a factorial here. So my handout on strategy says when you've got a factorial, you might want to look at the ratio test. So we're going to do the ratio test here. Right? And here our a sub n term, well, it's 1 over n factorial times x to the n power, all right? So let's look at the quotient of a sub n plus 1 over a sub n, and let's see what that simplifies out to. And then we'll take the limit. So a sub n plus 1, I substitute n plus 1 for n. So this is going to be 1 over n plus 1 factorial times x to the n plus 1 over my an, which is 1 over n factorial times x to the n. All right. And then we multiply by the reciprocal of the bottom, so we get 1 over n plus 1 factorial. We do want to keep our absolute value here around the x, and then that's going to be times the reciprocal here, so that's going to be n factorial on top and absolute value of x to the n on the bottom. And we can do a lot of simplifying with this. How is this going to simplify to? What's it going to simplify to? We're going to still have an n plus 1 in the denominator. What are we going to have on top, though? Absolute value of x. Right. So remember, n plus 1 factorial, of course, is n plus 1 times the n factorial. So the n factorial is going to cancel out and just leave us the n plus 1. And then we have one more power of x on top. So when we subtract the exponent, we still have a power of x on top. And then we know with the ratio test, the limit as n goes to infinity of this quotient, absolute value of x over n plus 1, needs to be less than the number 1. Well, I think we're going to be good to go on that one, aren't we? No matter what value of x we have, that denominator is going to keep getting bigger and bigger, so this limit here is equal to 0. So that's, of course, less than 1. So therefore, this thing converges no matter what our value of x is. So this converges for all values of x from minus infinity to plus infinity. We could also say the radius of convergence itself is equal to infinity. Okay, like that. All right. So that's our first example here of just using this Maclaurin or Taylor series. I think we can fit in a little bit more here. Let's look at the sine of x and do the same kind of thing. So here's the problem here is find the Maclaurin series for f of x equal to the sine of x. All right. Now this is where I'm going to do a little table, kind of like what I showed you there from the take-home quiz. It's going to have 3 columns to it. The first column is just going to be my value of n. The middle column is going to be whatever my nth derivative is of my function. And the last column, because I'm asking for a Maclaurin series, is going to be that nth derivative evaluated at 0. All right. So when n is equal to 0, we're talking about our original function. So in the middle column here, I'll put sine of x. And then in the other column, I'll put, well, the sine of 0, of course, is 0. All right. So let's do this for a few of these, and we'll see some kind of pattern. So when n is equal to 1, we're talking about the first derivative of the sine. So the derivative of the sine is the cosine of x, so I'll put that there. And then in the third column, the cosine of 0, well, that's equal to 1. Okay, let's go now to look at n equals 2. So now we take the derivative of the cosine that we just found, and that's the negative sine of x. And now we plug in 0, so negative sine of 0 is going to equal 0. Let's look at 3. And we have here that, okay, the derivative of the negative sine is the, what, negative cosine? And so let's plug in 0 there. So minus cosine of 0, and that's negative 1. And I'll do one more here. When n is equal to 4, we then take the derivative of the negative cosine, and that's sine. And then we apply 0 to that, and we get back to 0. All right. And this will then keep repeating itself. Notice that we are now back to our initial case here. All right. And so it just keeps repeating. Our next case will be this first case here. This case will then be the one after that. This case will be the one after that. We have a repeating pattern because of how the derivatives just keep repeating themselves. All right? So, let's look at our Maclaurin series. It's going to be f of x is equal to the summation. Here's our general formula. N equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n power. And then let's write out some of these terms here. Okay, for n equals 0, well, we just have 0 right up here. And it's x to the 0 power, so that's just 1. Then for n equals 1, we have that our value of the nth derivative is 1. And that's going to be 1 over, I'll put it 1 over 1 factorial times x to the 1 power. And then when n is equal to 2, we go to our case number 2, and our value again is 0. Let's go to n equals 3. Here's our case 3 here. Our value is minus 1. And then our factorial, though, is 3 factorial. And it's x to the 3 power. So I'm just writing out a few of these terms. I'll do a couple more so we can make sure we see the pattern here. When n is equal to 4, we're back to 0 again. So I'm just going to write 0. When n is equal to 5, I'm actually going to be back up here at this case right here, and that's going to be a 1 over 5 factorial times x to the 5th power. When n equals 6, we're going to be back to 0. And when n equals 7, we're going to be at negative 1 over the 7 factorial times x to the 7th. And I'm going to stop there. All right. So I've basically expanded this thing out by 8 terms just so we can see a pattern here. And what we have is this. Notice, first of all, that only the odd terms show up. The even terms all are 0. So we only have odd powers. So we're going to have a summation, n equals 0 to infinity. Now to represent only odd powers, let me put it over here. We're going to have x raised to the 2n plus 1. So when n is 0, that's going to be x to the 1st power. When n is 2, that's going to be x to, when n is 0, it's going to be x to the 1st power. When n is 1, it's going to be x to the 3rd power. When n is 2, it's going to be x to the 5th power. So we're only going to show the odd powers because the even ones all go to 0. And then in front of it here, we're going to have, notice these rotate. This is 1, minus 1, 1, minus 1. So I'm going to put minus 1 to the nth power there because it's going to rotate back and forth. And then that is all over the factorial of 2n plus 1 in factorial. 2n plus 1 factorial. So this here is the sine of x equals this. This is the Maclaurin series representation of sine of x. And if you look here at your important series right here, I don't use x. I decided to use the more general u as the variable instead of using x. And we see here that sine of u is the summation, n equals 0 to, it's the third one down, minus 1 to the n power times u to the 2n plus 1, strictly the odd powers, all over 2n plus 1 factorial. And I've written out here a few of the first non-zero terms, okay, like that. So that's the Maclaurin series for the sine of x, and it's going to converge. I'm not going to do that, but it's going to converge for all x, just like the other one did. Yeah?
So these ones are the solutions, these are all the Maclaurin and not the Taylor.
Right. If you see here, what we've got here all the way from until we get to the actual Taylor series, which is the one from the bottom, second from the bottom, they're all really Maclaurin series because it's all just u to the power. It's not u minus a to a power. Okay. But I also give the general Maclaurin series formula as the last one there. All right, and then we can do this, and I'm not going to go through it, but similarly, we can get the Maclaurin series for the cosine of x. For cosine of x. And that, the cosine is only going to have the even powers. Even powers only. So its representation is cosine of x is the summation n equals 0 to infinity. Again, we have a minus 1 to the n power, but now it's x to the 2n. So we only have even exponents, and it's all divided by the factorial of 2n. And then the first few terms of this, when n is equal to 0, we're going to have, what are we going to have? 1, x to the 0 power is 1, 0 factorial is 1, so our first term is going to be 1, and then when n is equal to 2, we're going to have x to the 2 times 1, or 2 factorial, minus 1 squared is going to be a positive 1. And then then we're going to have here what, this is n equals, let me rephrase that. This is n equals 1, not n equals 2. When n equals 1, we get x to the 2 times 1, or x squared. We get actually minus 1 here, sorry about that, instead of plus 1. And then it's 2 times 1 factorial, which is 2 factorial. So let's get rid of that plus there, sorry. When n is equal to the next number 2, then we have minus 1 to an even power, so that becomes a plus 1. This then is going to be x to the 2 times 2, which is x to the 4th. And then this is going to be 2 times 2 factorial over 4 factorial, etc. The next term is going to be minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So it's going to keep switching signs, plus, minus, plus, minus, plus. We're only going to have the even powers. And it does lead off with this 1. So notice that the cosine of 0, we know the cosine of 0 is equal to 1, and here we have it, it's 1 plus a whole bunch of zeros. So it remains consistent. The cosine of 0 does equal 1. All right. I think actually we've got plenty of time on Friday. Because today is just Wednesday, isn't it?
Yeah.
I think we have plenty of time on Friday to finish off this section and even then start just doing some random kind of just problems that kind of help start preparing for the test. So I think I'm going to just stop here for today. I know, I finally got a smile on your face. We're going to stop here for today and continue with the rest of the section then on Friday.
We didn't need that 6 minutes before 10 o'clock. That's 6 minutes after.
It's 10:06 on Friday. Right. Okay.